Hello, my name is Alan Kashishian, and I am a student at Gatech, and this is currently summer 2019, and I am enrolled in cyber physical systems. I will be presenting a paper that is called Through the Eyes of the PLC, Semantic Security Monitoring for Industrial Processes. The paper was first presented at ACSAC 14 proceedings of the 30th Annual Computer Security Application Conference in New Orleans, Louisiana, and it was held in between December 8th through the 12th in 2014. The paper was written by Dina Hadois Monavi, Robin Sommer, Peter H. Hartel, and Emmanuel Zambon. The article discusses how off the shelf intrusion detection systems or hardware that is used in the IT network should not be used for network security on the plant floor. Typically, hardware that is used to control a process in a plant floor, for instance a PLC controlling a filler machine, has concrete set points and programmable logic to control the process. Intrusion detection systems do not take into account the repetitive process of PLC control, which means if a process is occurring over and over again, the set points and logic controlling the process shouldn't change. An off-the-shelf intrusion detection system cannot stop an attack on a PLC's configuration and can cause product loss, product theft, and most importantly, bodily harm or death. This article discusses the creation of a passive intrusion detection system that creates variable-specific prediction models as a method to predict if the PLC configuration has changed. This is done by passively recording network traffic between the PLC and the devices the PLC is communicating with. Furthermore, the developers of the technology tested the equipment on 2 wastewater treatment plants. The intrusion detection system is shown to identify attacks on PLC process control. Testing is also being done to determine if this type of intrusion detection system can detect indirect attacks on field devices or sensors. The question is, why can't off-the-shelf intrusion detection systems efficiently protect the industrial network? Well, signature matching is the primary detection method of the attack, where a signature is a predefined pattern of network packet payloads that meets a previously identified attack. Unlike a conventional network, attacks happen on the plant floor or in the industrial network, far and few in between. Additionally, all processes that are connected to the industrial network are different by nature. For example, there could be a filler machine, there could be a packaging machine. Their processes are different, so they'll have different internal workings or set points and programmable logic. The unique nature of industrial control systems makes signature matching an unrealistic approach for intrusion detection. Recently, intrusion detection systems have added the support for industrial protocols like Ethernet IP and Modbus TCP. These types of intrusion detection systems add minimal benefit. They can protect against reads and writes to specific memory locations or prohibit certain commands from being sent from the PLC to a device or vice versa, and they can protect against buffer overflow, which means if I send a write to a memory location, I can send more data than is represented in the register and overwrite areas of memory that I shouldn't have access to. So this type of intrusion detection system can protect against that. However, it fails to detect malicious changes to process control over the industrial network. To fix this issue, intrusion detection systems can link directly to a PLC and monitor the variables or memory addresses. However, this direct link is very difficult to accomplish because of the proprietary nature of a PLC, which means the internal workings are held secret and the protocols they use for communication are their own and have limited documentation for recreation. The writers of this article have created a way to passively tap into an industrial network and not have to connect directly to a PLC. All they do is sniff network traffic, and they are monitoring the changes that are being sent from one system to another. This type of system is unintrusive, meaning that you don't have to make any changes to the PLC. It just taps directly into the industrial network and monitors the communication between the PLC and other devices. It is also scalable, meaning that it's just another network tap and a piece of software, and you can deploy it to multiple systems very quickly. This new type of industrial intrusion detection system creates a time series predictive model, which is based off of the packets being passed back and forth from a PLC to another device. Since the communication or process by nature is cyclic, the packets that are being passed back and forth should repeat in a time interval. Specifically, the process operations are extracted from the PLC's raw network traffic. A time series predictive model is created for each variable extracted from the packets. The timestamp and the variable's actual value allows you to predict the expected activity of the variable within the controller. For example, if there is a variable that is being monitored in the network traffic that stays stationary throughout the whole process, and on one occasion you notice that that value changes, that might indicate that there is a direct attack happening or the process has been changed on the controller. Furthermore, we can indirectly monitor field bus devices through the PLC by looking at the network traffic and monitoring the values of the sensor being passed to another system. And if we notice that the pattern has changed, we can determine or maybe conclude that the sensor has been tampered with or something has changed in the actual sensor configuration. I would just like to make a quick note that in a perfect world, the process that this new intrusion detection system performs would work. However, there is artifacts that are introduced to systems that are not malicious by nature that can throw up a false positive flag and say that the system is being attacked. So in a non-perfect world, this cyclic process actually has some variability. The writers of the article performed a case study to understand the wide range of possible network attacks on PLCs. The case study used Modbus TCP as the industrial protocol being passed between the PLC and other devices. The attacks were grouped in three separate categories. The first category was an attack on the IP or TCP level. An example they described in the article was manipulating the size of the TCP packet. The next category was attacks violating semantics of the Modbus protocol. For example, transmitting data that is outside of the range of the Modbus TCP protocol specification. The third category consists of legal actions by the protocol. For example, Modbus TCP sending a write or read command, but the semantics of the operation of the command is what's important here. For example, opening a valve at a specific time to release harmful gas into the industrial environment should never occur. Category 3 is the most difficult to detect because it needs semantic understanding of the process, or what is allowed or not allowed at certain times. The three categories can be broken down to three subcategories, which is 1, reconnaissance, or discover the process within the control. For example, figure out what variables do what. And number 2, direct control, or modify the process set points of the PLC process. For example, if the temperature needs to reach 75 degrees and you change it to 150 degrees, you could overheat the system. Number three, indirect control, or tampering the actual sensor or field bus network variable information that's being passed to the controller. For example, once again with temperature, tricking the temperature coming to the PLC as being one value when it's actually another. Three direct control attacks called Sabot, Stuxnet, and Carcano have highlighted the insufficiencies of current intrusion detection systems. All three produce legal commands that have malicious intent. For example, changing a set point to a value that can cause harm. The most famous and highly publicized attack of the three is Stuxnet. Stuxnet injected semantically meaningful commands into a highly specific plant environment. Stuxnet used valid commands to change a process. The malicious but legal commands spinned or rotated the centrifuge at a velocity that it could not maintain and physically damaged the system. Additionally, Stuxnet provided an indirect attack, which means it changed the values that were coming from the PLC to the display of the operators. So it was tricking the operators to believe that the centrifuge was spinning at the correct speed when in reality it was spinning at the wrong speed. With that in mind, the new intrusion detection system was created using three phases. In the first phase, network traffic is recorded and the variable data is extracted from the packet information. The second phase separates the variables into three different types. The third phase creates a time series predictive model on each variable. The model is used to show the deviation from the expected outcome and the actual outcome. The semantic meaning from the variables is extracted into two categories, which are process control and process awareness. Where process control is the variables and their timing based off of the actual physical process or PLC control. And process awareness is the variable data that's being passed to other systems, for example, to an HMI to display process information to the user. To test the system, a small testbed was created and used to validate the passive network monitoring approach. The goal was to mimic a wastewater treatment facility before they implemented the system into the real world. The testbed consisted of a PLC connected directly to an HMI. A simulation was created that mimicked a tank filling, heating, and discharging. The simulated virtual hardware consisted of a tank, heater, two valves, a level sensor, and a temperature sensor. The HMI was used to display and collect different measurement readings. For example, tank level, water temperature, valve 1 and 2 status, tank level alarms, and so on. Two attack vectors were also simulated. The first attack changed the level set points to overflow the tank. The second attack was indirect and it actually changed the sensor values coming into the PLCs or created false readings that was sent to the PLC that could trick the operator or trick the process. Using the test bed, the network traffic between the PLC and HMI was recorded. The Modbus TCP packet was broken down and the variable data was extracted. A shadow memory mapping was created. A shadow memory map is used to record the locations extracted from the Modbus TCP packet and the information or data that is associated to that memory location. The shadow memory mapping can be created to represent the actual memory mapping of the PLC through the network traffic. For example, if we extract the variables from a sequence of Modbus TCP packets, we can see what the value is, we can look at the memory address, and then we can see if that value is increasing or decreasing, and then we can semantically figure out what that process is. For example, the tank is filling or discharging. Furthermore, the variables extracted are categorized into different groups, which are variables that are used for control, variables that are used for reporting, variables that are used for measurement, and variables that are used for program state. Additionally, the variables are grouped into three categories. The variables are constant values or never change during the process. for example, a temperature set point. The variable is changed to only a distinct number of possible values, for example, different modes of operation, or the variable changes continuously throughout the process, for example, a temperature reading. With that in mind, the variable data extracted from our tank process or our test bed is semantically characterized into the different types of variables. The easiest type of variable extracted to semantically characterize is the constant value because it doesn't change throughout the process. The formula 2 to the power of k is used to determine if the variable is continuous. The k value is determined and tuned based on the specific system. For example, in the test bed, they use k equal to 3, which means during the process, if the variable changes to over 8 distinct values, that they know that the value is from a sensor and is continuous. If the value doesn't change more than 2 to the 3 or 8 times, then they know that the value is maybe an operation set point. The formula used could correctly determine the types of variables that was being passed from the testbed PLC to the testbed's HMI. To create time series predictive models from the variable data, two complementary techniques were used, which are autoregressive modeling and control limits. Where autoregression is used to create the time series predictive model, the control limits are threshold values that are 3 standard deviations above and below the mean that monitor the output of the time series predictive model and detect if the thresholds are exceeded. If they're exceeded, then a flag is raised. This model is used to predict continuous variable types. A flag is raised if the thresholds are exceeded or a large deviation between the predicted and the actual value is shown. Whereas a constant variable or a variable that has only a few discrete values can be flagged if a value is shown that does not meet the predefined discrete set of allowable values. The models are tested against the test bed by injecting two different types of attacks. The first attack changes the tank level set point, causing the tank to overflow. Then the second attack changes or tampers with the temperature level, thus stopping the liquid from heating up to the desired value before it is extracted from the tank. The results show that the autoregressive model is effective at detecting sudden changes, where control limits are good at predicting what the mean value of the process should be at the current time. The two direct control modification attacks were discovered by the system using the described techniques. With the validation of the hardware on the test bed, the hardware was introduced to two wastewater treatment facilities. Their setups were quite different than the actual test bed and much more complicated. Similar to the test bed, Modbus TCP was used for PLC to PLC communication in the wastewater treatment's plant floor. Using the prototype intrusion detection system, the PLCs were monitored for 3 days and 95% of the variables that were extracted were constants. 3% of the variables had subsets of a few discrete values, and 1% of the variables were continuous or analog values. This was run on multiple days, and it was determined that the values or variable types did not change. They did record some small changes in, for example, in constant values, but that could be an operator changing a set point or adjusting the set point to a new value. The system wasn't perfect. It also misclassified a few variables. Herein lies the problem with this approach. The misclassification of the variable or the operator changing the set point can directly affect the model and cause false positives. However, some of the error can be mitigated by taking or collecting more data. Instead of running the system for 3 days and collecting packets, maybe they need to run it for 2 to 3 weeks to obtain as many samples as possible. For continuous sensor readings, control limits were shown to have a negligible effect, and it was determined that time series models' predictive capability provided by the autoregressive model was the determining factor if a deviation had occurred. The autoregressive model was shown to perform very well on processes that occur cyclically and don't change from that cyclic process. The autoregressive model did have problems with floating point numbers because in Modbus TCP, the floating point number is split up into between four 16-bit registers, and different PLCs configure those registers in different patterns. So it's very hard for the extraction phase to connect the packets to create that floating point number. As of right now, the system that was developed has pros and cons, as described. It is good at discovering and detecting constant values and then the changes of those constant values. It is also good at detecting variable data that changes over time and modeling that data and creating a prediction. However, as described previously, there are other factors that come into play that add artifacts to the process that increase the false positive rate. This is only the first stage of creating this type of intrusion detection system. In the future, there are plans to create more robust systems that account for these artifacts and take more semantic meaning from the actual process to create the model. This concludes the presentation on the article Through the Eyes of the PLC, Semantic Security Monitoring for the Industrial Process. Thank you.